There we go. Right, so what we're going to cover in this presentation, we're going to look at what a feeder is. We're going to look at different ways of connecting antennas to feeders and feeders to radios. We're going to look at some different types of antenna. We're going to look at what antenna gain is and ERP. And we're going to cover that elusive subject of matching and SWR. We did touch on this last week, or in the last session even, but where we're actually going to go into that into a bit more detail. So feeders. Feeders are used to connect the transmitter and receiver, or transmitter or receiver, to the antenna. They can be what we call lossy or have a loss on transmit and receive. And the longer the cable or the longer the feeder, the greater the amount of loss. That is loss of the energy transferring through it because it's converted into heat. Feeder loss increases with the frequency. So thicker low loss cable is required for VHF and UHF. If you're using coax, there is another type called ladder line, which we'll look at in a moment, that is normally just one size, although I do believe there are variants of that. So we have the two types here. We have coaxial cable. This is the most common type of feeder used by radio amateurs. It's unbalanced, and we'll go into what that means a bit later. It consists of an inner conductor, okay, then there's some plastic, and then there's an outer braid, or known as the screen, and that keeps the signal in this central conductor. With the twin line feeder, or the ladder line, this is a balanced feeder. Again, we'll cover more on that later. And it has equal and opposite signals in the two wires. There is a constant separation between the two wires. The distance between the two is the same all the way along the cable. So we then have ways of connecting the feeder to the antenna and to the radio. And we have different connectors that can do this job. Antennas and feeders are connected by various different types of connectors. The plugs and sockets for RF should be of the correct type. There are different types and different values, but they should be of the correct type. And we'll go more into that in a moment. There are 4 types, which will appear on the next slides. These are all used with coax. And the screen of the coax must be correctly connected to ensure the RF signals don't get into or out from the cable. This is something that the actual connecting of it is something you will cover in intermediate. The actual soldering it onto the cable, that will be covered in intermediate. So the first 2 types we have here are the PL2559 and the End Connector. They look fairly similar, but they are very, very different. The PL259, it says here, is common for HF. There was a stage when VHF and UHF were going over to End connectors. I personally have noticed that they are starting to come back to the PL259. The reason for this is the End connector is a nightmare to put onto a piece of coax. It's an absolute nightmare. Whereas the PL259 is relatively straightforward. The 259 indicates the diameter of the plug, and the PL means that it's a plug. The socket it goes into is an SO2359 or 249. You'll know it. It begins with SO. It's gone out of my head for the moment. Another 2 types that we will be looking
239.
at is 39. 239, thank you. SO239. The SO stands for socket. The 239 is the diameter. Thank you, gentlemen. The next socket we're looking at is the BNC. It's bayonet locking. I love these because they are so easy to connect onto coax, but they aren't used ever so commonly. All connectors, it's got it specifically on the BNC, but all connectors should be 50 ohm. The BNC is also used in other standards, like it's used for CCTV and things, and they tend to use the 75 ohm version, and that has a different type of pin in the center. But yeah, there is BNC. There is also SMA. SMA is a thread locking connector, and it's very often found on handheld radios, and there are some slight variants on handheld radios as well of this. So if you're going to use an antenna that for a handheld that's got an SMA connection on it, you need to make sure you've got the right one. Okay, we're going to look at some antennas now. Antennas convert electrical signals into radio waves and vice versa. They are designed for specific frequencies, and it's different sizes for different bands or different frequencies as well. So in general, the longer the wavelength or the lower the frequency, you need a larger antenna. Remember that wavelength and frequency are directly proportional. So that if you have a long wavelength, you have a lower frequency, and the antenna is directly related to the wavelength that you're operating on. So we have here we have the main 5 antenna types. We have a Yaqui. Another, I don't like this picture of a Yaqui particularly. But if you imagine a TV antenna that you might have on your house, that's a form of Yaqui. It's essentially a dipole in the middle with a reflector and a director, and you can have multiple directors along it. We then have a dipole here. Again, this is another bad photo. You can't see it clearly, but it basically there's 2 elements, one sticking out each side, and they're normally balanced. So that's a dipole. You have a 5/8 wave, okay, a quarter wave, and you have a long wire. We're going to cover these in more detail in a moment. So a standard dipole. So this is a picture of a half-wave dipole. Your feeder point is here. So that's where you attach your coax to, and then you will have one element sticking out each side, and the total length of the antenna will be half of a wavelength. So if your antenna is 10 meters long, you can work on the 14 megahertz band, or the 20 meter band. So obviously the 10 meters is half of 20 meters. And this is a balanced antenna. When we're looking at antennas, we can draw a pattern of how the antenna radiates. This is a polar pattern, and you can see that where we've got the antenna here, the radiation is radiating equally out of both sides. So the maximum radiation is directly opposite the center of the dipole at 90 degrees. It's the furthest point out. When mounted vertically, the half wave is omnidirectional. That means that the radiation goes out in all directions. So it's not, when it's horizontal, as it was previously, the radiation there is coming out the top and the bottom, or if you're looking down on it from the top, it's going out to each side. When you've got a vertical dipole, it's going out every single side. So if that was a 3D image, it'd look like a big donut round a pole. We then have a quarter wave ground plane. This is a vertical antenna, and it is quarter of a wavelength long. So for example, it would be 50 centimeters to work on the 2 meter band. There are 4 horizontal wires, and these are called radials, and they form a ground plane, which is like a big mirror that reflects the radiation both into the main element and away from the antenna. The signals are omnidirectional once again, so it will come out in a circle around the main element. And a 5/8 wave ground plane antenna. Again, these are vertical and omnidirectional. They're 5/8 of a wavelength long. They have better signals towards the horizon. The coil at the base is to do with matching coax. So again, the coax is 50 ohms. This allows the antenna to match that coax. And they're very often used for VHF and UHF. You don't tend to see them on HF so much. And they're also used in mobile. So you can see the image here doesn't have the ground planes out the side. That is because the vehicle underneath is acting as that ground plane. And we also have end-fed antennas. These are essentially, it's just a long piece of wire. It's unlikely to be the correct length for the waveband you're working on. So it needs to be matched. We'll go through this very shortly. And they're more likely to cause interference to other devices like other radios, tellies, things like that. And they're more likely to cause the interference to those. And lastly, we have the Yaqui. These are directional. I'll show you what that means in a minute. They are focused. They focus the signal mainly in one direction. It is essentially a dipole. So here we have what we call the driven elements, and that is a dipole. I did not mean to do that. And behind it, you have a reflector, and then you have your directors, okay? And these push the signal in that direction, the direction of the arrow. So here we have the Yaqui pattern. If you imagine, so this is where the driven element is just here. And behind it, you have a reflector, and the reflector would go through the side lobes. And then your directors would be positioned within this bubble, and it pushes the signal in this direction. Okay, we're going to go on to antenna gain and ERP. So the Yaqui antenna, for instance, focuses signal in one direction, and it has a higher gain than other antennas. Gain is the amount of power actually getting out of the antenna. And antennas have a measurement of gain in decibels relative to the half-wave dipole. This table will be provided in your exam, but it is an important table because when you're trying to work out the amount of power leaving your antenna, it's useful to refer to this, and I'll show you why in a minute. So if you have a gain of 3 decibels, that's twice the power leaving. So I'll show you what we mean now. The directional power of the antenna is expressed as ERP, or effective radiated power. The power applied to the antenna feed point is multiplied by the antenna's gain. So we have an example down here of 10 watts times 3 decibels equals 20 watts. Now, 10 times 3 is not 20. But the reason it equals 20 is if we go back to the previous slide, the gain is actually times 2 when it's written in 3 decibels. Okay, so if it's 3 decibels, it's twice the amount. So when 10 is times by 3 decibels, you're actually timesing it by another 2 watts. So it's 10 times 2, which is why we get 20. You feed a 3 decibel Yaqui with 10 watts and 20 watts will radiate in the primary direction. For example, so to put this into a more visual term, if you've got a torch, it's got like a mirror around the back of the bulb that focuses the light to make it appear brighter in one direction. The other thing you do have to take into account at this point is the losses within your coax. So you may have your radio set to 10 watts. That doesn't necessarily mean you're going to have 10 watts at the feed point of your antenna. So you would need to measure it at the antenna point so you know how much power is getting into the antenna. We're going to look at polarization. That is essentially a posh word for which way up you have your antenna. Do you have it horizontal or vertical? Yaqis can be vertically or horizontally polarized. And most VHF, UHF is vertical, with exception of single sideband that likes to be horizontal. At VHF, UHF, the receive and transmit antennas should have the same polarization. This is less of an issue at HF as polarization may be changed in the ionosphere. If you are on VHF, UHF and your polarization isn't the same, that doesn't necessarily mean that a contact cannot be had. I very often transmit on a vertical antenna on single sideband, talking to people who are on single sideband on horizontal antennas, and we still make contact. Okay, we're going to look at matching and SWR. When you're connecting an unbalanced feeder to a balanced antenna, you need a balun, which stands for balanced and unbalanced. Earlier I mentioned that the coax feeder is unbalanced. So between the coax and the antenna, you would need to put a balun, which is a ferrite ring with wire twisted round it, and it's all connected into the feeder and then into the antenna. The feed point. The connection point of the feeder to the antenna is called the feed point. Antennas are designed for specific frequencies, and the feed point impedance that should match both the feeder and the transmitter. The impedance of an antenna at the feed point is related to the dimensions of the antenna and the wavelength of the applied signal. In amateur radio, the feed point is nearly always 50 ohms. Oh, the impedance of the feed point is always nearly 50 ohms. SWR. If the impedance of the antenna does not match that of the feeder, energy known as standing waves will be reflected back down the feeder. The worse the match, the more energy gets reflected back. This can be quite a complicated subject, but this is the simplest way we can put it at this level. A standing wave ratio meter, or SWR meter, is used to test whether an antenna presents a correct match. We use an SWR meter to measure the flow of the power back from the antenna, and a ratio of 1:1 is an ideal or good match. So, for example, an SWR of 2:1 means that 10% of your power is being reflected back. The higher the SWR at the transmitter, i.e. much greater than 2:1, indicates the feeder or antenna mismatch, which may damage the transmitter. If you've got a device that is meant to push out energy, and energy is being fed back into the part of it that's meant to push energy out, there is going to be damage. So what can we do about that? Each band ideally requires a different length of antenna. If the antenna is correct, the correct length for the band you want to work, there will be a match. If not, you need to use an antenna matching unit, nearly always referred to as an antenna tuning unit. These can correct the mismatch, ensuring that there is no damage to the transmitter. We did touch on these in the last session. They are an important part of your shack, unless you have an antenna that is resonant on the frequencies you wish to work. And an ATU is commonly used when you're working multiband. So for instance, my antenna, I have one long wire and I use it on nearly every amateur band, or every HF amateur band. So I could not do that without an antenna matching unit. There was also a device called a dummy load, and this can be helpful when you're when you're trying to test your station. This is a screened resistor, and when buying, please check for the correct value and suitable power rating in watts. It can be very easy to get the wrong one for what you're trying to do. You connect this in place of your antenna to your transmitter to allow the transmitter to be operated without radiating a signal. This can be useful if you are looking for RF leaks in your rig or in any other cables. It just takes the antenna out, but allows you to still push energy out of your radio. Well, I've just had a message saying I've got to hurry up. So we've got a summary now. We've looked at feeder types of unbalanced coax and balanced twin feeder. We've looked at connector types of PL2559, End plugs, BNCs, and SMAs. We've looked at antenna types, a dipole, a quarterwave, 5/8 wave, Yaqui, and end-fed. We've looked at antenna matching units. We've looked at polarization, i.e. horizontal and vertical. We've covered standing wave ratios, and we've looked at how to work out the ERP of your antenna. And we've looked at balance to match the balanced antenna to the unbalanced feeder.